Welcome everyone. This is Circular Dynamics lecture number 10, and we are dealing with motion in a vertical circle. I hope all of you recollect this. Just giving you a quick recap of what has happened up till now. We have seen that the motion of a body on the outer surface of a cylinder or a sphere or a ring or a disc, and we have seen that if you push the body from the top, the body that rests on the top at any angle theta, if it makes, the velocity is given by a simple formula root over 2gr into 1 minus cos theta. Just find the value of cos of this theta, the vertical angle, and you should be able to find out the velocity. And if you know equation number 1, equation number 2, which we have done so many times, and equation number 3, you should be able to find out all the unknown quantities. Velocity is already known. You can find out normal reaction from equation number 2. You can find out tangential acceleration from equation number 1. You can find out centripetal acceleration because you know centripetal acceleration is v squared by 2. So far, so good. What's next? What should I do here at this point? There is one more thing that could be asked in this question, and let us now get our attention to that thing, and I'll give you a formula for that. And I'm sure that once you know the formula, you should be able to find out something from that formula as well. Again, I would be giving you the formula, and we might not be deriving the entire result, because deriving the entire result will not help your cause, especially in NEET. In the class for JEE, I would be deriving it because they would know, they would want to know. It's essential for them to know this. But for you guys, it is not important. So the topic is still motion in on the outer surface. We have to write one important point here in the same thing. Now, what we had done up till now, and let me draw the circle once again. This is my vertical circle, and the body is at the top. The center is O. The center is O, and the radius is R. Now, up till now, what has happened is your body of mass M is at the top. The point I have called is at A, and I have given it a very gentle push. Things are remaining same. Now remember, this is just kept on the top of the surface. It is not attached to this surface. So it is not like your roller coaster. I hope everyone has sat sometime on the roller coaster. Now when you are on a roller coaster, that roller coaster is moving on rails, but that roller coaster is attached to the rails. It cannot leave. It cannot leave the rails and fly in air. Your train ka wheel and track, train is only kept on the track. It is not attached. I mean, there is a small protruded part in the wheels which sort of attaches it, but it is not physically attached to it. If you talk about roller coaster, if this is the rail, then the roller coaster sits like this. So it is attached. So it moves like this. It just cannot leave the track. I hope you understand it. The roller coaster cannot leave the track. Here, what is going to happen is this is just kept on the top of the surface. So this is a round surface. It is just kept on the top of the surface, and I give it a push. Now, when I give it a push, it obviously slides down. My question is, will it keep sliding down? Will it just go like this? Will it go like this? Or will something happen somewhere in between? Will it just keep on sliding along the circular path? Or will something happen somewhere in between? What is your answer? Can you tell me? What do you think will happen? Will it keep on sliding on the circular track? Or something will happen somewhere? Anyone can give me an answer. I hope question is clear to everyone in the class. Abhiram, Tanu, in the online class. Does the block keep on sliding? Like this. Remember, it is not attached. It is not attached. Now, since it is not attached, we call such motion as not confined to a circular path. So I would also add the heading here, and I would like all of you to do the same. Go back to the previous class. This I always add after we have understood this. This is the motion on the outer surface. And remember, this motion is not confined. This is not confined to circular path. I hope you understand the meaning of this thing. I have already told you this is not confined to circular path. That means it is not attached to the circular path. It can very well leave the circular path. If it is confined to a circular path like your roller coaster, the motion is similar, but something changes. And I'll try to make you understand what changes. But here, right now, what I'm asking for you to tell me, and I would like some answers quickly because I can't wait till eternity. I don't have time till eternity. What happens? Does the block keep on sliding or something happens? Remember, this is motion on the outer surface, not confined to a circular path. What happens? Anyone? Online class, offline class, will it keep on moving like this along the dotted line? Or will something happen in between? Offline class, can you listen to me? Can you see me? Can you hear me? Can I have some response? Online class, do you understand the question? Does the block keep on moving on the circular path? And yes, the answer is no. Yes, the answer is no. It will not keep on it will not keep on moving like this. At some point in time, what will happen? At some point in time, when this block reaches a certain position, let us call this position as position B, it will lose contact. It will lose contact. It has to lose contact. What are we supposed to understand from here is what angle will it lose contact? It will lose contact at some point. At what angle does it lose contact? So remember, the angle at which the body loses contact, angle at which the body loses contact, what is that angle? Cos of that angle, cos of theta is 2 by 3. That is the angle at which the body loses contact. Or I can say theta will be equal to cos inverse 2 by 3. And this is one information that you should always remember. If a question comes, it would be a straightforward question and you can write the answer straightforward. One more thing can be asked. What is the velocity with which it loses contact? So velocity at this point where it loses contact, velocity at point B where it loses contact. This velocity is given by root over R into G into cos theta. We always know, we know the value of cos theta. The value of cos theta is 2 by 3. So now you also know the velocity at which with which the body loses contact, and the answer is 2 by 3 Rg. Remember this value. Remember this value, cos theta is 2 by 3. It's a very important result, and this result will appear at many times in this circular path. Theta is equal to cos inverse 2 by 3 or cos theta is 2 by 3. This is a very important result. Very important result. And it keeps on coming over and over again. I'll give you a minute to write the information that I've given you. Remember, the body is kept on the top or outer surface of a round body. May it be a cylinder, it may be a sphere, it may be anything circular. At some point in time, since it is not confined to circular path, it is not attached to the circular path, this body will leave contact. At what point it leaves contact? Cos of that theta is 2 by 3. The velocity with which it leaves the contact is root over Rg cos theta, and it is equal to 2 by 3 Rg. Remember, this point of contact, this angle of contact does not depend on what body is kept. It does not depend on whether it's a cylinder or a sphere. It does not depend on the radius of the sphere. It does not depend on all those things. It is a fixed value, and the value is cos of this theta is 2 by 3. You have to remember it till you give your exam. Even after that, don't forget it. I'll give you a minute to note it down. If you have any problems, please come up. Welcome back, everyone. I hope you have noted down the formula. Yes or no? I hope everyone has noted down the formula. Let us move ahead and move on to the next heading. Move on to the next heading in this motion on a circular track. Now, the first motion that we saw was motion on the outer surface. So if I can't use this. The first motion that we saw was motion on the outer surface. Let me take this and try to make some sense. Here, if this is a circular thing, the motion was happening on top of this. Tung, 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 tung. This is motion on the outer surface. Motion on the outer surface. Tung, 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 tung. Everyone understands this. What is going to happen now is the next heading. And what can happen next? The next heading is motion on inner surface. Motion on inner surface. Now, what is the inner surface? See, this is the inner surface. Inner surface. This one was outer. This is inner. Now, in this inner, we also have outer. So, look closely. Up till now, the motion was happening here on top, outer surface. We're moving on the outer surface. Now, it will move here on the inner surface. Inner, outer, inner, outer, inner, outer. Simple as that. The next heading is motion on the inner surface. Now, this motion on the inner surface is similar. So I'll just write slash mass attached to a string. Mass attached to a string. Both the motions are similar. Both the motions are similar, and both are examples of motion which is not confined to circular path, CP. Not confined to circular path. That means they are free. They are not attached. We'll say, sir, mass is attached to a string. It is attached? No, it is not attached. It is attached to the string, yes, but it is not confined to a circular path. It can leave the circular path. I'll try to make more sense of it. First, just write the heading motion on the inner surface or motion of a mass attached to a string. Both are examples of motion which are not confined to a circular path. First of all, let us make some sweet diagrams. Physics is nothing without a diagram. If you can solve any physics problem without drawing a diagram, either you are plain lucky or you have done some mistake, or you are a genius. If you're not in the three categories, you have to draw a diagram, which I'm going to draw right now. So I'm going to draw two diagrams here. Oops. This one, gentlemen, and this one, gentlemen. Oops. Things don't always turn out the way they are supposed to turn out. I'll just use it again. Dung, 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 dung. Oops. Oh, I hope all of them look similar. They are circular. Okay. Now, this first case is something kept like this. Again, this thing could be your cylinder. This could be your spherical shell. Remember, it has to be empty because motion has to take place inside of it. This could be your ring or anything that looks circular, which has got a circular groove, vertical circular groove. Now, it has a center and it has a radius R. Now, the case could be case A. This case A is motion on the inner surface. This is the case of motion on the inner surface. Now, how the motion is going to take place here? I'll keep a block at the bottom, block of mass M, and the block is going to move like this, or the block is going to move like this on the inner surface of the shell or cylinder or whatever you call it. I hope you understand how it is moving. Everyone understand this? Can I have some raise hand? It's going to move like this on the inner surface. Yes or no? Can I have some raise hand that we understand this? From the class, I'm not getting any response. The mic is on. You said yes, sir, yes, sir. Why did you say yes, sir, yes, sir? Just to keep quiet for the entire class. Good. That is A. Then this point B, oops, wrong color. Very peculiar about colors. Okay, this is point B, mass attached to a string. And listen to what I say very, very carefully, and you will understand what is the difference between the two. Obviously, nothing seems to be attached. It just kept on inner surface and it is moving. In this, gentlemen, case number B, what seems to happen is we have an origin O, obviously, and instead of a circular track, this is a circular track on part A, I have a string. And at the end of the string, I have a bob of mass M. This, gentleman, is a string. This, gentleman, is a string. And let us say the length of the string, since we are talking about string, therefore we talk about the length. The length of the string is L. This is not a difference between the string and the circular track. Instead of calling the radius as R, since length of the string is given to you, I am calling the length of the string as L. This L is nothing but the radius of the circle R. Just a matter of L or R, doesn't matter. What I want you to understand that both the motions are similar or different in one way. If I draw the free body diagram of the gentleman on the right, no, gentleman on the left, which is A. If I draw the free body diagram, what do I see? I see a weight mg. If I draw the free body diagram for gentleman on the right, which is gentleman B, I also see a weight mg. Now this weight mg is omnipresent because this gentleman is on planet Earth, Mother Earth. Now this weight mg is obviously not moving it in the circular track, because if mg would have made it move on a circular track, everything will move on a circular track, but everything doesn't move on a circular track, everything falls. Oops. Because weight is downward, so it falls. The weight is not going to move it on a circular track. The difference between the two, or you can say in some cases, in some sense, similarity, is what is making them move on the circular track. Now I ask you this question. Gentleman A and gentleman B. Gentleman A is on the inner surface of a circular track. Gentleman B is attached to a string of length L. What is making gentleman A move on the circular track is definitely not its weight. What is making gentleman B to move on a circular track? Definitely not its weight mg. Can anyone give me an answer? What is making both of these gentlemen move on a circular track? This gentleman is also going to move like this. He will go up like this side, or he can go up like this side. Simple pendulum is just like the motion of a simple pendulum, but simple pendulum only moves like this. This will go like this, up, 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 and come back, up, 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 and come back. So it will complete a full circle. Can anyone tell me what is making gentleman A and gentleman B to move on this circular path? What force is making them move on this circular path? Anyone with an answer? What force? What is that thing? That is making them move on this circular path. Anyone has an answer? I would be pretty glad to know your thoughts. Yes. If I draw the free body diagram of gentleman on the left, you will see a normal reaction N coming from the circular track. This normal reaction The blue one is coming from the circular track. This is coming from the circular track, which is, since if there is no track, it cannot move. The normal reaction coming from the circular track is doing the job. What job? Doing the job of moving it on this circular path. Normal reaction N is responsible. Now I ask you the question again. What is making the gentleman B move on the circular track? What is making gentleman B to move on the circular track? Can I have some answers? Gentleman A, normal reaction N. What about gentleman B? What is making him move on circular track? Reply fast. I'm waiting. And yes, the answer is the tension T. The tension T, which is coming. The tension T, which is coming from the string. String is trying to pull it. This tension T is making it move on the circular path. That is the difference between the two motion. On gentleman A, normal reaction, which is trying to push it up. Normal reaction is trying to push it up. Normal reaction is trying to push it up. Normal reaction is making the body move on this circular track, which is pushing it up. In case B, the tension in the string is trying to, instead of calling it push it up, I'll call it pull it up. Tension T is trying to pull it up. I'll write it. Tension is trying to pull it. Tension is trying to pull it. Here, normal reaction is trying to push it. Do we understand this? Can I have some raise hand that we understand this? Normal reaction will always push. Tension will always pull. Normal reaction is pushing it. That is making it move on a circular track. String is trying to pull it. That is trying to making it to move on the circular track. Can I have some raise hand that we understand this? Online class, offline class, can I have some raise hand that we understand this? Okay. Now again, we had discussed that this motion is not confined to a circular path. Now, what do I mean when I say this? You can realize, you can understand that in case number A or in case number B, both the cases, when I'm pushing this ball up, this block up, once it reaches a certain height, if it is able to reach that height, once this block reaches a certain height, this block can fall. This block will lose contact. This block will lose contact at some point. So it will fall down and it will not be moving on a circular path, and therefore this motion is not confined to a circular path. Similarly, when I'm moving this block with the help of a string, this string cannot push, it can only pull. And at some point in time, this string, if the velocity is not that much, and we'll see how much is that velocity, if that velocity is given less than a particular value, at some point in time, When it is moving, dung, 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 at some point, it will become loose, the tension will become zero. Here, normal reaction on the left hand side, normal reaction would become zero. On the right hand side, tension will become zero. If normal reaction becomes zero, which is trying to make it move on a circular path where it's not there, the body will lose contact and it will fall and not follow circular path. Similarly, if tension becomes zero in the right hand side, this body will not follow circular path and it will leave the circular path. Therefore, we call such a motion as not confined to a circular path. Similar thing happened in the first case. In the first case, we saw when the angle becomes cos theta is 2 by 3, it loses contact. When it loses contact, it leaves the circular track. Same thing will happen in case number A, same thing will happen, can happen in case number B, and therefore we call this motion as not confined to a circular path. I'll give you a minute to note down whatever I have said. Everything that I say, I will not write it on the board, on the screen. You will have to make your own notes in your own language. It may not be English, it may be any language that you are comfortable with. Write it. Whatever I've said, I'll be back in a minute. I'll give you a minute, 2 minutes. Welcome back, everyone. And I hope you have noted down the points that I have said already. Case A, normal reaction is going to make it move in a circular path. Case B, tension is going to move it on a circular path. And this motion is not confined to a circular path. So we'll write some important notes and you will have to remember these points, and I'll try to summarize everything in those points. So let us first write the first point. Why it is not confined to a circular path. So remember this point. Point number 1. If T or N becomes 0, if T or N becomes 0, the particle leaves the circular path. If T or N becomes 0, the particle leaves the circular path. We will be writing notes and then I'll try to explain them. This is quite clear. If T or N becomes 0, the particle leaves the circular path. I've explained it. Now, what could be the condition that this T or N never becomes 0? What should be the condition that this T or N never becomes 0? And we can think logical. See, we can divide this entire circular motion into two parts. You can divide this entire circular motion into two parts. And I'm going to make that division by this red line. This red line. Anything below this red line, anything below this red line is the lower half of the circle. Anything above this red line, anything above this red line is the upper half. Do we understand this? Can I have some wave of hands that we understand this? Lower half, upper half. That simple. Let us also name some points. Let us also name some points for our better understanding. So either I name them on figure A or I name them on figure B, doesn't make any difference. We understand that in figure A, whatever is being done by normal reaction. In figure B, whatever is being done by tension. Here it is N, there is T, rest all is same. Let me name, and I name it like this: A, the lowest point; B, right hand side ka center point; C, topmost point; D, यहाँ का point, and again back to A, नीचे वाला point. I hope everything looks similar. Now I will be putting more points here as the class progresses. By the end of the next class, you might have more points coming here. But let us now concentrate on this A, B, C, D. BD is your diameter line, as I can see. Anything below BD is your lower half. And I've only drawn on one circle. The same thing could be done on the other circle. Anything below BD or DB is the lower half. Anything above DB is your upper half. Now let us analyze this entire motion: lower half, upper half, lower half, upper half. Now, I hope you have written this. I hope you have drawn this. It is very simple: A, B, C, D. Tongue, tongue, tongue. One line. Below that, lower. Up above that is the upper part. Now we were talking about point number one. We have discussed that if T or N becomes 0, the particle leaves the circular path. Done and dusted. Now I ask you, I have seen two halves, lower half, upper half. Where do you think, common sense, no physics, where do you think that this T or N can become 0? I'll repeat my question. Where do you think? Don't think about physics. Physics is just what you see right in front of you, that is physics. You can understand it, you can analyze it. You can find a fault. Chemistry, you cannot. So, again, a general knowledge question. Where do you think can T or N become a 0? Your answers. Lower half, upper half. Where can T or N become a 0? I'm not talking about the case where the string breaks. I'm not talking about the case where the circular track is breaking. Let's be practical. Things are not going to break. Things are going to remain intact. Where do you think the tension T or normal reaction N becomes 0? Can become 0? Anyone can give me an answer? Where do you think? And I've shown you the upper half, lower half, A, B, C, D. Where do you think the tension or normal reaction can become zero. Anyone with an answer? I cannot wait till eternity. Where do you think T or N can become zero? Yes, the answer is T and N. T or N can never, and I am using the word never very strongly, T or N can never what? Become, can never become zero in the lower half. And I'm again very strongly using the word lower. Oops. Wrong color. Can never become zero in the lower half. Do we understand this? In the lower half. When I say lower half, I mean below the line BD. Below the line BD. Lower half, below the line BD. Tension or normal reaction can never become zero unless and until the string breaks, which is not going to happen, or this circular path breaks. T and N can never become a zero. Do we understand this? Can I have some raise hand that we understand this? What about the offline class? What about Tanu? Do we understand this, Bacha? Can I have raise hands from you guys? The analysis is the most important part here. Offline class, do we understand this? I'm not getting any signs from you. Okay, done. Now, if T or N can never become zero in the lower half, where can they become zero? T or N can only become zero in which half? Now it is very simple to understand. Only in the upper half. Only in the upper half. So it's only in the upper half that you can have T or N becoming zero. T or N can only become zero in the upper half. Upper half above BD. Upper half above BD. That is the only region in which T or N can become zero. Now, if I ask you, what about the line BD? I've talked about the lower half. I've talked about the upper half. In the lower half, tension T cannot become zero. In the upper half, tension T or normal reaction N can become zero. What about the line BD? Can tension become zero at the line BD? And the answer is yes. The lowest point where T or N, I'm talking about both, can become 0 is B or D. B or D. These are the lowest point where your tension can become 0. Below that, it can never become 0. Above that, it can also become 0. The lowest point where it can become 0 is point B or point D. Am I clear with this? Can I have some raised hands from everyone in the class? Online class, offline class? I'll give you a minute to write this down. I'll be back after a minute and I'll wind up the class for today. Welcome back, everyone. And I hope you have noted down the points. We've come to 4 point. The lowest point where T or N can become 0 is B or D. T or N cannot become 0 in the lower half. T or N can only become 0 in the upper half. Now the question is, on which quantity does it depend? Whether T will become 0 at point B, whether T will become 0 at some other point. Say, for example, if I go back to your diagram, between B and C, in this entire region, I have infinite number of points, literally. I have infinite number of points between B and C. Tension cannot become 0 below C, yes. Tension can become 0 at B, that is the lowest point, yes. But between B to C, which is the upper half, tension can become 0 at any point. And as you can see, there are infinite number of points there. Where will tension become 0 between B and C? What is the deciding factor? What is the deciding factor that decides where this tension is going to become 0? And the deciding factor is speed or velocity at point, wrong color, speed or velocity at the lowest point, and the lowest point is A. Speed or velocity at the lowest point A decides if and where T or N becomes 0. I hope you understand the meaning of if and when. T or N may not become 0. Listen to my words, everything I won't be able to write. T or N, case number 1, may not become 0. Sorry, case number 2, point number 2. T or N can never become 0. T or N can become 0 at point B. T or N can become 0 at any point between B and C. What is the deciding factor? Whether or not it becomes 0, or it does not become 0, or it becomes 0 at point B or point C or any point in between. The deciding factor is the speed or velocity at point A, and we will begin our class with that thought in our mind in the next class, that The deciding factor is the speed or velocity at the lowest point, and we'll begin our class paying special attention to speed or velocity, magnitude of velocity at point A, and we'll see at what speed what happens. On this note, I am going to wind up this class. The class is dismissed. If you have any doubts, you can come up. Till next time, till we meet, have a nice day. Take care. Bye bye.